Today we'll talk about learning by recording cases. This is our first topic of learning, one of the fundamental elements of knowledge-based AI. It is also our first topic in analogical reasoning, often considered to be a core process of cognition. We'll start talking about recording cases in a general sense. Then we'll discuss a specific method for retrieving cases called the nearest neighbor method. We'll generalize this method into the k-nearest neighbor method and end by talking about complex cases in the real world. To see how learning by recording cases might work, consider a world of blocks, colored blocks with various shapes and sizes, 6 blocks in all. Now let us suppose that I were to give you a question. So based on your experiences in this world, what do you think is the color of this block? What was your answer, David?
So based on the shape, size, and orientation of this block right here, it looks like it's most similar to the black block on the left, so I'm going to say that the block is black.
You're right, David. Of the various blocks given here, this block best resembles the black block, and therefore the best guess would be that this is in fact a black block. This is an example of learning by recording cases because 6 cases were recorded in the agent's memory. So now when a new problem comes along, then the agent gives an answer to that new problem based on the cases that it already had recorded in its memory. It simply sees which case most closely resembles a new situation and gives the answer to the new situation for that most closely resembling case. This gives a visualization of what is happening in learning by recording cases. There is a new problem A shown by the color here, and memory contains a large number of cases, again represented by the different colors here. So we retrieve the case B that is most similar to the new problem A. In this particular case, we are deciding by color. And whatever was the solution to B, we apply to the situation A. While this visualization is useful, it's still very abstract. Let's think in terms of some practical, everyday examples. So you get up in the morning and you want to go for a run. You put on your sneakers, you have to tie your shoelaces. Well, how do you tie your shoelaces? That's a new problem. But of course, you have tied shoelaces many, many times earlier. So you have a memory of tying shoelaces to different kinds of shoes. That's all stored as cases in your memory. So as you start tying the shoelaces for the shoe today, you simply retrieve the closest matching case and apply it. None of us really thinks very hard in the morning about how exactly to tie shoelaces. If we were to do it, it would take us a very long time. So in learning by recording cases, memory directly supplies us with the answer. We don't have to think about it.
So another example of this that comes to mind is in programming. Oftentimes in programming, we deal with the same type of problem over and over again. So I might imagine I'm starting out a new program and I'm writing a program in Java. So I'm given a new problem of creating a new program in Java. All I'm going to do is look back at my memory of cases and retrieve another case of starting a new program in Java. And I'm going to apply the solution to that program directly to this one. In this case, it's going to be something like when I'm starting a new program in Java, last time I started with public static void main. I'm going to apply that solution directly to my new problem, and it works. The solution can just be transferred directly to the new problem without any kind of modification. Then later in developing that same program, I might hit, for example, a null pointer error. I'm going to use that null pointer error as a new problem and use it as a probe into my memory. I'm then going to retrieve a case of when I encountered a null pointer error in the most similar program I've worked on, and then that's going to give me a solution that I potentially can apply directly to my current problem. So for example, the solution to the last time I encountered that same error might be to run the program in debug mode and allow it to tell me exactly what variable is null at the time of execution.
That's a good example, David. And we can even try to generalize it to medical diagnosis. Imagine that you went to a medical doctor with a set of signs and symptoms. So the doctor is faced with a new problem. What is the diagnosis for your signs and symptoms? The doctor may even have a number of cases recorded in her memory. These are the cases she has encountered during her experience. So the doctor may select the most similar case, the most closely resembling case, which in this case might be B, and say that I will apply to A exactly the same diagnosis that I applied to B. So a case then is an encapsulation of a past experience. And learning by recording cases is a very powerful method that works in a very large number of situations, ranging from tying your shoelaces to medical diagnosis. Let us look at this learning by recording cases a little bit more closely. Implicit in our discussion so far has been the notion of most similar or most closely resembling. But how can we operationalize it? How can we make it more explicit? So once again, here is the world of various colored blocks. And we can represent these various blocks, back to the notion of knowledge representation, we can represent our knowledge of these various blocks in a two-dimensional grid, the width of the block and the height of the block. So the blue block may lie here, the red block here, and so on. So when a new problem comes along, we may represent it on the same two-dimensional grid. In this particular case, the new problem may be represented at this particular dot. Now, given all the cases in the new problem, we may calculate the distance between the new problem to each of the previous known cases. Once we have calculated the distance between the new problem and each of the previous cases, we can simply select the case which is closest to the new problem. This method is called the nearest neighbor method. Now we need a way of calculating the distance between a problem and a case. One measure of the distance is called the Euclidean distance. Here is a formula for the Euclidean distance. The Euclidean distance between 2 points, x of c and y of c, which define the case, and the x of n and the y of n, which define the problem, is given by this formula. Now we can easily calculate the Euclidean distance between each of the cases in the new problem, and this table summarizes the distances. Given this table, we can very quickly see that the case of the black block is closest to the new problem, and therefore one might give the answer that the new block is also black in color. So the nearest neighbor method is one method of finding the most similar case or the most closely resembling case. Let us do an exercise together. Given the block shown here with the width of 0.8 and height of 0.8, what do you think is the color of this block? What answer did you come up with, David?
I plotted the block on the same axis that we plotted all the other blocks on, and I found that it would be plotted right here. Calculating the distance between this block and all the other blocks, I found that red was just a little bit closer than orange or black. So I said the block is red.
So in this problem, we are dealing with a two-dimensional grid because here two coordinates, x and y, are enough to represent any one point. In the real world, of course, problems are not that easy to represent, and one might need a multi-dimensional space in order to be able to represent all the cases in the new problem. Let's examine a problem like that now. So here is a map of a small portion of Long Island in New York. Imagine there is an automated car that can navigate the streets of this neighborhood. It comes from the factory with the 6 cases bootstrapped in it, A, B, C, and so on. For the timing, assume that the car navigates its way in this neighborhood solely by the method of learning by recording cases. So all it can use is these cases that it knows about. Now suppose that we have a new problem. The new problem is how to go from Q to this end destination denoted by the arrow. What route is most similar to the new problem? What do you think, David?
So personally, I said that D is the most similar case. There are a couple cases that are closer to the origin, like A and B, but they both go in a very different direction than we're trying to go with Q. Similarly, E ends even closer to Q, but E starts much further away. D looks like it's the one that both starts closest to Q and ends closest to Q.
D here is the right answer, but let us think how we can program an AI agent to come up with this answer. Now we can try to calculate the most similar case to the new problem based solely on the origin. The two-dimensional grid here tries to represent both all the cases and the new problem. Of course, we can also calculate the similarity of the new problem with the old cases based on destination. This two-dimensional grid captures the cases and the problem based on the destination. We can compute the Euclidean distance between Q and all the cases based on the origin, shown here. And we can do the same thing based on the destination, shown here. If we focus only on the origin, then the B case seems the closest. If we focus solely on the destination, the E case seems the closest. However, the B case is not very good when we look at the destination, and the E case is not very good when we look at the origin. How then might an AI agent find out which is the best route of all of these choices? How might it decide that D is the best route? Earlier we had this formula for calculating the Euclidean distance in 2 dimensions. Now we can generalize it to many dimensions. So here is a generalization of the previous formula for computing nearest neighbor. In this new formula, both the case and the problem are defined in k dimensions, and we'll find the Euclidean distance between them in this k dimensional space. So this table summarizes Euclidean distance between the cases and the new problem in this multidimensional space where we are dealing both with the origin and the destination, and where the origin as well as the destination are specified by the x and y coordinates. Looking at this table, we can very quickly see that D and not B or E is the closest case, the most similar case to the new problem Q. This method is called the KNN method, where NN stands here for nearest neighbor, K nearest neighbor method. This is a powerful method, as simple as it is. Of course, it also has limitations. One limitation is that in the real world, the number of dimensions in which I might want to compute the distance between the new problem and old cases might be very large, a high dimensional space. In such a situation, deciding which of the stored cases is closest to the new problem may not be as simple as it appears here. A second difficulty with this method is that even if the new problem is very close to an existing case, that does not mean that the existing case's solution can or should be directly applied to the new problem. So we need both alternative methods of retrieving cases from memory and methods for adapting past cases to fit the requirements of the new problem. That is called case-based reasoning, and we'll discuss that in the next lesson.
For this assignment, talk about how you might use the notion of recording cases to design an agent that can solve Raven's progressive matrices. You might think of cases in a variety of different ways here. For example, each figure in a problem could be a case. Each transformation between figures could be a case. Or more broadly, each problem that your agent has encountered in the past could be a case. As part of this, you'll also need to think about how to evaluate similarity. If you're using figures, how do you evaluate the similarity between two figures in a problem? Or how do you evaluate similarity between two transformations in a problem? Or more broadly, how do you find what problem that you faced in the past is most similar to the new one you're facing now? So today we discussed a learning method called learning by recording cases. In learning by recording cases, we file away individual cases we've encountered in the past in order to use them for future problem solving. We talked about the nearest neighbor method as a way of finding the most similar case to the current problem that we faced in the past. But in the real world, this can often be very difficult. So we talked about using nearest neighbor to find very complex similar cases to our current problem, such as our navigation example. However, there's still a lot of limitations to this method. Oftentimes, just executing a solution we've used in the past doesn't work. And oftentimes, we have to store cases based on qualitative labels instead of numeric labels. These weaknesses will be addressed in our next lesson when we talk about case-based reasoning. There, we'll add adaptation and evaluation into our process and start to be able to use cases in a much more thorough and robust way.
Learning by storing cases in memory has a very strong connection to cognition. Cognitive agents like you and I are situated in the world. Our interactions with the world have certain patterns of regularity. The world offers us the same problems again and again. If you think about it, the kinds of problems that you and I deal with on a routine, everyday basis are the same problems that occurred yesterday and the day before. Tying shoelaces is a good example of that. When we have to tie shoelaces, none of us thinks a lot about how to do it. Memory supplies us with the answer. We don't think as much as we think we do. If you recall, we had drawn a cognitive architecture earlier that had 3 components in it: reasoning, memory, and learning. When we think of intelligence, we typically focus on the reasoning component. We think intelligence is to do with reasoning, with solving problems, with decision making. To some degree, that is true. But learning by recording cases shifts the balance between the components. It says that learning is very important, and so is memory. We record things in memory, and then memory supplies us with the answer so that we don't actually have to reason as much as we think we need to. Please write down what all you learned in this lesson in this box, and thank you for doing it.